So hello everyone, my name is Supradeep, and yeah, today I'm going to present my DA623 project which actually stands for Computing with Signals, and my topic for the presentation is Range's phenomenon, numerical conditioning, and the power of the orthogonal polynomial. In this experiment, in short, I will actually compare two different polynomial bases. The first is the monomial basis, which actually produces a Vandermonde matrix, and yeah, the secondly, I will actually compare it with a Legendre polynomial basis, which actually consists of orthogonal polynomial on the interval -1 to 1. And yeah, other than that, I will also compute the condition number of the x transpose x using a function which I will show on in the later stage. And yeah, the condition number actually measures the numerical stability. And yeah, what we can actually say is a large condition number actually means a large condition number actually means that a small changes in the data can actually cause a large changes in the solution. So yeah, let's start with the presentation now. In the first cell, as you can see that I have actually imported all the necessary libraries such as NumPy, Matplotlib, and yeah, these are modules inside NumPy to actually perform the linear algebra and the polynomial operation. And yeah, in the second cell, I have actually defined a Ranges function, which is actually a smooth continuous and yeah, perfectly. And yeah, in short, it is actually a perfectly well-behaved kind of function. And yeah, if any kind of instability appears in our result, it will not be because of the function itself. It will be because of the polynomial approximation only. And yeah, in the third cell, as you can see that I have actually generated some kind of sample data points which are actually noisy in nature. And yeah, as you can see that I have actually generated 15 of such sample points in the interval of -1 to 1. And yeah, just to actually simulate the real world measurement, I have also added small amount of Gaussian noise as well. And in this plot, as you can see that there is some kind of red points, and there is a bell-shaped curve, and the red points actually represents the observed data. And yeah. This bell-shaped curve, and this bell-shaped curve actually represents the true function. And then what we can say is, if the noise is actually small, we can actually expect a reasonable regression model to actually approximate the function really well. And yeah, other than that, we I have actually created this fit polynomial function only, as the name actually suggests. It is this thing actually generates the Vandermonde matrix manually, where each column actually corresponds to x raised to power 0, x raised to power 1, x raised to power 2, or x cube till dot 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 till x raised to power t. And yeah, after that, I have also computed the least square solution using the normal equation, which is actually w is equal to x transpose x inverse and then x transpose y in this equation, as you can see. And yeah, after that, I have also computed the conditioning number of the x transpose x. And yeah, what we can say is, if the condition number is actually large, the matrix inversion actually becomes really numerically unstable. uh, and yeah, in the next one, I've actually fitted the whole data in the monomial basis. As you can actually see, for the degree is equal to 2 whereas degrees. In this blue curve, as you can see, we cannot even see it. What that actually means is we actually observe some kind of underfitting here. And in the degree 5 and in the degree 5, as you can see that the uh approximation actually improves a little bit. For degree 10, we can see that the oscillation actually appears to actually begin near the boundaries. And yeah, by oscillation 15 or 20, the polynomial actually exhibits extreme oscillation, especially near the -1 to 1 interval. And yeah, the whole phenomenon actually known as the Ranges phenomenon, which I'm actually trying to explain. These and yeah, just to actually notice in these numbers and the plots, the condition number actually increased dramatically as the degree also increases. This actually simply indicates the x transpose x is actually becoming really ill conditioned. Now just to actually summarize this whole thing, the mathematics of the least square has not been changed, but the numerical instability has been deteriorated severely. So now let's see the condition number growth. As you can see that the plot actually uses a logarithmic scale to actually show the growth of the condition number. And here we also observe a near exponential kind of growth as the degree of the polynomial actually increases. And here what we can say is then is an ill conditioned system actually amplifies noise and the floating point error. And yeah, this actually explains the extreme oscillation that are being observed. And then in the cell 7 and cell 8, I have actually compared it with the legendary basis. So let's start with that. Just to actually repeat that the legendary polynomial are actually orthogonal in the interval of -1 to 1. And yeah, the orthogonality actually means that the columns of the design matrix are actually less correlated. And yeah, this actually reduces the numerical instability during the inversion, which actually simply means when the columns are near when the columns are actually nearly independent, the matrix inversion actually becomes more stable. Uh, and yeah, let's actually see this plot. Well, we actually increase the degree of the polynomial in the legendary basis. As and yeah, as we have actually repeated the same experiment as before with a different kind of basis. What you can see is the oscillation near the boundaries are actually reduced. And yeah. And yeah, the condition number are actually much smaller as compared to the monomial basis. So in short, what we can actually say is that regression objective is actually identical, and the only change is the choice of the basis vector only. And yeah, in the let's come to the last cell. In the last cell, I have actually compared the conditioning capacity for the both of the bases, both of the bases corresponding to the increasing polynomial degree, and yeah, increasing the conditioning number in the log scale. So what we have actually done is in this comparison, it clearly shows that the orthogonal polynomial actually significantly improves while conditioning. And yeah, in the Ranges phenomenon, it is not purely about overfitting; it is also deeply connected to the numerical conditioning and the basis selection. So that's all about this whole thing. And yeah, just to actually summarize this like whole like project in this like demonstration, what we have actually seen is that a high degree polynomial regression using the monomial basis actually leads to severe yield conditioning, and the like condition number of the X transpose is actually grows like rapidly, which actually amplifies the noise. And yet it also produces some kind of unstable oscillation. And yeah, by actually switching to orthogonal basis such as the legendary polynomial, we actually significantly improve the numerical stability. Uh, yeah, the like least square method itself remains like mathematically sound only. And yeah, however, the like choice of the basis actually determines whether the computation is actually stable or unstable. So yeah, in short, this actually highlights the importance of the numerical conditioning in the like signal modeling and the like computational mathematics. So that's all about my presentation. Thank you.